Barbecue. Well, it's a day off. It's fun. You get to goof off a little bit. Okay, so that's a transverse wave. So notice the particles are going up and down. See? So if you think about who's a fisherman, when you go fishing, right, you have a bobbin. Did you ever go cane pole fishing? Huh? No, you never did? God, you missed out on everything in life. It's great fun. I've done it. And you know, or whatever you have fishing. And then you have a bobbin, right? If you're just in a lake, right? So the waves oscillate, don't they? Don't they oscillate? You see little ripples in the water, so the waves travel. But the bobbin doesn't move. It more or less stays in the same position, you see. It just goes up and down. It might move a little bit, kind of oscillate. But basically the bobbin's going up and down. Like, so the bobbin goes up and down. The particles of the wave go up and down, but the wave travels through. The wave itself moves. So what then is moving? What is moving in the wave? If the particles that carry the wave are going, they're not really changing position, right? They oscillate with simple harmonic motion. Say, what is moving in the wave? Particles? No, the particles stay in the same relative position. Right. That's what we're saying. If you take a rope, do you ever take a rope? And, you know, they have those exercise things where you do like that, and the wave travels. But the thing, the particles that make up that heavy rope, right? They basically stay in the same position. I mean, they might move a little bit, but basically they're not moving anywhere. They're just going up and down. Yeah. So what is traveling? Yeah. Actually, yes. The energy travels. The energy input. So waves carry energy. See? That's why waves are so important. They carry energy. They're energy transport. Mechanical waves carry mechanical energy, and electromagnetic waves carry electromagnetic energy. Okay? So, you know what we should do, which I didn't do, we should try to define a wave. So let's see. One of these days I'm going to write this out in advance. So a wave, let's see if I can define this in a way that makes sense. A wave is a disturbance in a medium whose particles oscillate in simple harmonic motion.
Energy that travels.
Okay. You want me to define that? There's lots of ways to do it. I don't particularly claim that this particles oscillate in simple harmonic motion, and this is very bad. And between particles between the said particles govern the speed of the wave with okay, so I'm going to go like that. So it's not very good. But it's a disturbance in the medium, meaning the disturbance usually we're referring to is you put some energy into the medium, right? So you throw the pebble into the water, you disturb the water, you put some energy, and that particles that comprise the medium oscillate in simple harmonic motion. So if you look at the water molecules, they're moving in simple harmonic motion, okay? And the interaction between the water molecules defines I shouldn't say the speed, I might say the transmission. That might be a better word. Of the wave, or the speed of the wave. How the wave propagates, let's see, through the medium. Govern, this is the way, how the wave propagates. Maybe that's better. So for example, right, in water, you have, water has hydrogen bonding or something, I don't know, who's a chemist? It has a natural relationship between water, right, hydrogen bonding, that governs how the wave propagates. So the water molecules are moving in simple harmonic motion, but they're transmitting the wave to the next one, you know. This one moving like this causes the next one to move, which causes this one to move. But that lateral movement is governed by how water molecules interact with one another. In a string, which is a solid, right, it's a different thing, right? As opposed to water. Water's a little more dampening. Or in a gas, right? You have a wave in a gas. Now, in a gas like air, right, sound waves move longitudinally, okay? And so the air molecules oscillate in the same direction as the wave. So if you make a sound, see, you wake up the crowd. You create some energy here, don't you? No, but you make it louder or lower. Okay, it's very good. It's very good. Soft applause or loud applause. But you use some energy here, and that's transmitted. And air molecules oscillate in the same direction as the waves moving this way with the air molecules. So the air molecules oscillate around an equilibrium point, you know, they're temporarily pushed this way or that way. So when sound goes out, you get what they call over here. They have it here. I think I have a picture of it. Here. You get a region where the gas is denser, right? So the wave, this is dense, this is denser, this is less dense in this region, less dense. So you have dense, and if you were to plot density versus position, all right, it looks like this. I think it was drawn right. It's denser here, and then less dense, and then more dense. So the air, when we say denser, what we mean is, I mean, the gas follows PV equals nRT, right? But, so the density is higher than it would be if it was just still air. Because the PV equals nRT governs the density of air, right? The gas law. But when you create some energy for sound, explosion, or something, you compress it. And this region is denser than it normally would be, and this region is less dense than it would normally be. And it's that change in density that's moving through the air. Okay, and it has velocity. Well, we kind of boxed that up, so difficult. Let's see what we can get out of this. So, what's the equation? We have an equation. Y, here it's the wave, we're changing the Y value as a function of X and T, right? So, with time, the wave moves on. So, for a given X position, right, here might be the peak, and then later it's halfway down, and then it's at the trough, and then it's rising. So this is some position X. So it's a function of position and time, right? Because over time, the wave is moving. So Y, the Y value changes, and this is the equation that governs it. Looks somewhat similar, but it's different. Y max is sine kx minus omega t. Where k is our spring constant, and x is position, and omega is angular frequency. Here's the equation. Now, so you have, in this case, so you have y displacement. It sort of reminds you of oscillation. So here's y. This is y max. It's a sine function. And you have something called the angular wave number, which is k is 2 pi over the wavelength. This is a different k. And I think that's right. And omega is 2 pi times the frequency, or 2 pi. Would you avoid doing that in the class? Thank you. Could you wait till the end? No, I don't know why. So you have angular wave number, which is 2 pi over the wavelength, and what they call the angular frequency, which is the same as what we have before, 2 pi times the frequency. So here they go through and explain that to you. K is equal to 2 pi over the wavelength. Here they're describing why it's a function of x and y, how the wave moves with time. Here's the peak, it's moving with time. Okay, so we have the notion of a wavelength. You know what a wavelength is here? From peak to peak, or trough to trough, or 0 to the same point, right? That's the wavelength. And then you have the frequency, which is how often does a wave come by, right? So you're standing there watching the waves come in, huh? every second or whatever it is, you know, that's the frequency. And you have a period. But it's not an oscillation, it's a wave motion coming in, okay? So that can be a little confusing, but anyway. Now, so you have wave number and you have period, angular frequency, and frequency, and they go through that for you there. And we get similar equations. Now here's a checkpoint. The figure is a composite of 3 snapshots, each of a wave traveling along a particular strength. The phases are given by 2x minus 4t, 4x, 8x minus 16t. Okay. So, what do they want to know? Which phase corresponds to which wave in the figure? So what's the equation? It's kx minus omega t, right? So the equations are what? 2x minus 4t, 4x minus 8t, 8x minus 16t. So which is which there? What was K? 2 pi over the wavelength. Omega is 2 pi times the frequency. So which has the largest frequency?
The last one?
Yeah, that's right. It has the largest frequency. And so what does that correspond to? Which one? This one? Or the big one?
Whatever.
Hmm?
The one that, 2.
Which one has the greatest frequency? Repeats
The
itself.
one, the one,
Yeah,
the one.
one. Yeah, it throws you off. Okay? Yeah. And then the smallest one would be
So, 2.
2, and then the third one is in the middle. Now, one thing I neglected to mention, I always forget this. I always forget to mention something. What's the basic physics principle? Physics. The velocity of a wave is a constant. For a given set of conditions. Okay. So, for example, the velocity of sound is a constant. And what's the conditions? What is the gas? Or what is the medium carrying the sound? And what is the temperature? So for a given set of conditions, I should say, but I really should say, for the medium. For a given medium, right? The medium that carries sound is air, right? In a vacuum, you don't have any sound, right? So the speed depends upon the temperature and the density and the gas. Right? So if you have a different gas, like that's the old joke, right? The guy swallows the helium and then he speaks and it sounds real funny. Because he's got a different type of gas, right? The sound is carried differently. Anyway, so the rope, how thick is the rope? How thin is the rope? You know, a thin rope, you know, what's the tension in the rope? The rope is taut. If it's really tight and you pluck it, it travels quickly at speed, right, the wave. But if it's really loose, a slack rope, speed is really slow. How thick is the rope? You know, thick ropes have slow wave thick. So it depends, but for a given set for the medium, when the medium is fixed, then speed is fixed. Okay. Now, what they do here, is they go through and they define for you the velocity, right? The velocity turns out to be omega over k, or wavelength times frequency. Okay, so this is the wave speed. So that means we have a wave. You know, if you look at this wave, this is the velocity of the wave as it travels through space. Frequency times the wavelength, or the velocity is equal to omega over k. Okay. That's dx dt. Well, so let's look at, here's a very important one. Let's look at this thing here. We'll call it a day. Here's an equation of three waves. They want you to rank them according to their wave speed. And then the maximum speed perpendicular to the wave direction of travel, the transverse speed. Right? So, here's a wave. So the first one says, what's its speed this way? And the second one says, what's its speed this way? Right, when you have the rope where you know, the exercise plays where you go up, down, then when you go like that, how fast can you go up and down? Or how fast does the wave travel this way? The first one is that way. So what we say, the velocity is equal to what? Wavelength times frequency. And this number k is what? 2 pi over lambda. And omega is 2 pi times frequency. So V will be large. So what is? What we say? It's also V is also omega over k. So V will be large when omega over k is what? The velocity will be large when omega over k is, somebody, what? Steve, you're done. Well, if this number is large, what does this ratio have to be? stuff. No, stop thinking and listen. I wanna find which one of these has the largest velocity. So I need to compare omega over k, right? And when this ratio is large, the velocity will be, when this ratio is large, when omega divided by k is a large number, okay? Suppose it's 27 million. Then the velocity will be, no, you're all mixed up. When the ratio is large, the velocity will be large. They're equal. They're equal. You confuse yourself. No, you're all mixed up. I'm telling you, people don't understand ratio. They don't understand the ratio. They don't understand one number divided by another. So let's figure this out. What's omega over k for this? This is the first one. No, for the first one. What's omega over k? Huh? 2 over 4? Is that right? What's the next one? Somebody.
4 over 3.
4 over 3. The last one?
1.
3 over 3. This one's 1. 1.3. A half. Which one has the highest speed? Number 2. Then number 3. Then number 1. See that? It's just simply omega over k. Okay. Then what? I want the biggest speed vertically. What am I given? I'm given displacement in the y direction, so how do I get velocity out of that? How do I get velocity? From displacement. How do I get velocity from displacement? Huh? How do I get velocity from displacement? The vertical velocity. Anybody? Carlos.
That's the equation.
How is x related to velocity? First derivative. What's dy dt? Which one has the largest dy dt? Okay. It'd be 2 times 3 is 6, right? The middle one is 4. The other one is 2 times 2, 4. Who's confused about that? Sanasa, are you with me on that? Okay. So they'll all be a cosine function, right? But it's the derivative of this on the inside. We're just taking the absolute value. Okay. It's the speed. Speed's always positive. Well, somehow you managed at least to never get it right. Maybe look at